Today we are going to be covering concept 2.4, lipids are hydrophobic molecules, from Principles of Life, second edition for the AP course, Hillis et al. This is in textbook pages 29 through 31. Now, when we talk about lipids, we're referring commonly to, we probably heard fats is what we've called them in the past before, but specifically they are hydrocarbons, meaning they are composed of carbon and hydrogen atoms primarily that are insoluble in water because of many nonpolar covalent bonds. Okay, so we have a lot of carbons, a lot of hydrogens. Insoluble means that they don't mix with water. When they do come close together, they form weak but additive, meaning a lot, very, very many with a small force, but being added together, creating a relatively large force called the van der Waals interactions, which hold them together. So lipids are also used in storing energy in carbon-carbon single bonds and carbon-hydrogen single bonds. They do play structural roles in cell membranes. Of course, lipids do make up the phospholipid bilayer. And they are the source of body fat in animal bodies as a primary form of thermal insulation and also for cushioning and long-term energy storage. So when we look at our lipids, okay, we start with triglycerides or simple lipids. Okay, so again, these terms fats and oils that we typically have heard. Fat generally refers to any lipid that is solid at room temperature, and oils are liquids at room temperature. So we're going to assume 30 degrees Celsius or approximately 80 degrees Fahrenheit. Now, they have very little polarity and are extremely hydrophobic. I'm sure you all remember from your elementary science classes, when you pour oil into water, it immediately dissociates. It separates. It does not matter how much you shake that container. They will not mix together. Okay, so these triglycerides, they consist of 3 fatty acid chains. These are nonpolar hydrocarbon chains and 1 glycerol group. It's an alcohol with 3 hydroxyl groups together. The synthesis of these triglycerides involves 3 condensation reactions. And again, that is going to remove water. You can see this shown in figure 2.11 on the bottom of page 29 in your book. So as we bring these together, we have glycerol, this alcohol right here, our 3 fatty acid chains. We will connect them, and as we do so, we remove 3 water molecules. So the fatty acid chains can vary in length and structure. Now, if it is said to be saturated, that means that all bonds between them are single. So if we go back for a second, we can see these are all single carbon bonds. We don't have any double bonds here. Okay, if they are unsaturated, that means we have 1 or more double bonds present, and this causes a kink in the chain, and it does prevent molecules from packing close together because it does change their overall shape. So because the unsaturated fatty acids don't pack tightly, they have low melting points, and this is what gives rise to our ones that are liquid at room temperature. So you can see here we have extra virgin olive oil like you use to cook, and over here we have salted butter, and this is actual butter, this is not margarine. We're going to have a discussion in class about the difference between butter and margarine and how it is made. Okay, so when we look at these individual fatty acid chains, okay, so this is our most simplistic one. We have palmitic acid. We have this long chain right here. You can see single carbon bonds all the way down. Because of that, we can have this very close proximity of one to the other. Now, opposed to this, once we have the introduction of a carbon double bond, in this case we have 2 of them in linoleic acid, it creates this kink or this bend in the molecule. Because of that, these individual molecules, they can physically not be as close together as they were able to with a saturated fat. Okay, so fatty acids are what is called amphipathic, meaning they have a hydrophilic end and a hydrophobic tail. Okay, a water-loving and water-fearing or hating tail. So these phospholipids that we've talked about that form the cell membrane, we have 2 fatty acids and a phosphate group bound to a glycerol. The phosphate group has this negative charge, making that part of the molecule hydrophilic, so it wants to stay away from water. Okay, so we can see on page 31 in your text, We have this shown here. This is figure 2.13. We can see the hydrophobic tails that are not attracted to water. And then we have the hydrophilic head up here that is attracted to water because it is polar. Okay, we have our glycerol group here, okay, and our phosphate group. Okay, so this is an example of a phospholipid molecule. Another phospholipids, the amino acid serine, the sugar alcohol, uh, inositol, or other compounds can be attached to it. Okay, so these will pack closely together and then ultimately form a lipid bilayer, which you can see in figure 2.13b. So this phospholipid bilayer provides a membrane for the cell. Now, in doing so, it also allows for the connection of oligosaccharides, oligoproteins, like we talked about in the previous lesson. Okay, so we see this generalized model here. So in an aqueous environment, the tails right here will stay away from water and the heads will interact with water, forming this bilayer. So recall in chapter 1, we briefly discussed the fluid mosaic model. So this is not static. It's not like a wall. This does move around freely. Have any questions, make sure to put them in the comments below and be prepared to discuss them in class.